Take a moment to gaze at the night sky. Everything you see, the stars, the band of the Milky Way, even distant galaxies, only accounts for a tiny fraction of what's actually out there. Shockingly, dark matter outweighs all the stars and planets combined, shaping our universe in ways we're only beginning to understand. Welcome to part 3 of our series on star formation, black holes, and now galaxy formation. To recap, in part 1, we explored how stars form from giant clouds of hydrogen combining for billions of years before dying off as white dwarfs. Or, if they're big enough, explode into a supernova, leaving behind a neutron star or even a black hole. In part 2, we focused all of our attention on black holes, whose gravitational wells are so intense that not even light can escape. Now, we'll see how these stars and black holes become the very building blocks of galaxies, ultimately giving rise to solar systems like our own. To start, let's rewind to about 400 million years after the Big Bang. As discussed in a previous video, we saw how the universe started off primarily as hydrogen and helium. Around this time, dark matter made up around 63% of the universe's mass, while the rest were various types of particles. Today, dark matter makes up around 27% of our universe, and the rest is dark energy, which is responsible for the constant expansion of space. The remaining 5% is only atoms that we're familiar with. So, why is dark matter so crucial? It doesn't interact with light, so it's invisible, but it does have mass. Wherever dark matter clumps, its gravity pulls in normal matter, seeding the formation of galaxies. Think of these dark matter clumps or halos as scaffolding for star-forming gas clouds. Over time, these clouds condense into stars, planets, and eventually entire galaxies. And in the center of each of these galaxies, there's often a supermassive black hole, especially early on in the universe's life. That said, galaxies don't appear as a single isolated system. There are two main ideas behind greater galaxy formation. In the bottoms-up approach, smaller structures like dwarf galaxies merge to combine larger ones. These mergers can happen at any stage in the process, from dark matter halos fusing together to even fully formed galaxies colliding. In the top-down approach, a colossal dark matter halo, sometimes called a cosmic pancake,
I'm a pancake,
fragments into smaller different galaxies. Both the tops-up and bottom-down approach can coexist, shaping the cosmic web we observe today. Galaxies come in all shapes and sizes, and are typically classified into 3 categories. Elliptical galaxies range from nearly regular to elongated. They're packed with older stars and see little ongoing star formation. Spiral galaxies, on the other hand, are characterized by disks and winding arms with active star formation. Our Milky Way is a prime example, teeming with younger, brighter stars in its spiral arms. Lastly, irregular galaxies lack a clear shape or bulge and are usually found early on in the universe's life. Spiral galaxies are the most common types of galaxies and exhibit a particular trend. When physicists measure a galaxy's rotation, the outer regions rotate faster than expected if only visible matter were present. In fact, rotational speed stays nearly constant the farther out you go, suggesting that there's far more mass present than what we can see. The leading explanation is dark matter, which stabilizes the galaxy's rotation. To put it into perspective, on one hand, the visible matter in the Milky Way weighs in at around 10 to the 11 solar masses, where one solar mass is the mass of our sun, 2 times 10 to the 30th kilogram. So our galaxy is pretty freaking heavy. On the other hand, dark matter might weigh around 10 to the 12 solar masses, which is 10 times more than the visible matter that we can see. Within one of those spiral arms, our Milky Way's own Orion arm, lies a modest hub of 8 planets, dwarf worlds, and icy debris. Our solar system orbits around 26,000 light years away from the galactic center, anchored by our beautiful sun. Beyond Neptune's path, a donut-shaped Kuiper belt extends to 50 astronomical units, where 1 AU is the average Earth-Sun distance, which is about 150 million kilometers. Far beyond the donut, a spherical Oort cloud may reach up to 100,000 astronomical units, harboring more than 1 trillion frozen bodies. Overall, invisible dark matter halos sculpt galaxies, which in turn forge stars, and in one quiet spiral arm, our own sun and even planets. Every atom in us was minted in these stellar furnaces. As Carl Sagan said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Thank you for tuning into part 3 of our 3-part mini-series on star formation, black holes, and galaxy formation. If you enjoyed this journey, make sure to smash that like, subscribe, and notification bell so you'll get a cookie and you won't miss the next thing that we talk about, like dark energy or even quantum gravity, because that's what we do here. We talk about fun stuff, and that's it. That's all I got for you. See ya. I'll never see you ever again, maybe, unless you hit subscribe. But until then, I don't know what's gonna happen. I might just go no green screen, and now you get to see what my house looks like, and that's weird now, isn't it? Yeah. Jank.